So this is the second podcast in chapter 12, and I apologize that I'm going to jump around a little bit, but it's hard to have access to a smartboard and stuff and write on it at home, and that's what we need for a bulk of the chapter to show equations and solve them. So I'm going to jump around a little bit today. We are still on page 1 of your notes, and we talked about chemical kinetics, and they are about studying reactions. And then we talked about ways to make a reaction happen faster, and we used the analogy of how to get a prom date. And so there were 5 things we could do to make a reaction happen faster. We could shorten passing periods to force the molecules to move faster. And so this is, or the people to move faster in the hallways, but this would be like increasing the temperature of the reaction. We can shrink the hallway, and that would be analogous to increasing the pressure and decreasing the volume of a reaction to force the molecules to come into contact with each other much faster. And then you could bring in more boys and girls, or increase the number of molecules reacting. You can also increase the surface area of a molecules, and that was the not have girls travel in packs idea. And lastly, you could be a matchmaker. You could add a catalyst, and that is essentially something that makes the reaction go faster but doesn't interact or become part of the bonds of the reaction. So all of this is kind of going back to what we call the collision model and how atoms and molecules react. We have to think about the fact that molecules must collide in order to react, and they must have enough energy to react. They must have enough energy to move around, and they must collide at a certain orientation. And that is a big key factor, is they might hit each other, but if they're not hitting each other with the proper orientation, the transfer of energy won't occur. So they have to have enough energy to collide. When they do collide, they have to collide at a certain orientation. And then when they collide, they still need to have enough energy. They call that the activation energy to create the products. I'd like to take a look at the 5th one, the catalyst part, a little bit closer today. And so that's where my jumping around comes into play. So I'm going to have you turn to page 7 of your notes under section 12.5, where it's called reaction mechanisms. And we're going to take a look at that. So I'll give you a minute to flip to page 7 of the packet where it says section 12.5 reaction mechanisms. And I will find this slide is slide 66 on your PowerPoint. I'm going to find that really quick, and we'll start there in a second and see what we can do. So 2 criteria must be met for a reaction mechanism to be plausible. And the sum of the elementary steps must give the overall balanced equation for the reaction, and the mechanism must agree with the experimentally determined rate law. We can only really, at this juncture in chapter 12, look at the first thing, the sum of the elementary steps. And that's just because you haven't talked about rate laws and what they mean and how to write them yet. So this might be a little confusing, but we'll get kind of the basics of it, and we'll come back to it again after we learn rate laws. And then hopefully it's just a good review for you. So there's 3 varieties of individual steps, or molecularity, or reaction mechanisms. The first reaction mechanism that we can look at is something called unimolecular. This reaction involves 1 molecule. We call this first order. That's not going to make any sense to you yet, so don't panic. But this is like a decomposition reaction, if you remember types of reactions from last year. A bimolecular reaction involves the collisions of 2 species. They call that a second order. Again, that's not going to make much sense, but that's okay. But you can see there's 2 reactants. They collide, react to make your product. And lastly is called a ternary molecular. And this is a little bit trickier to see, and it's actually a lot harder. It's very rare, I should say. And you don't see this as much happening. Why? Because if you think about it, you have 3 molecules that have to come together and collide at the correct orientation. And that is a lot more difficult probability-wise than having 2 molecules collide and hit each other. So this is a little bit more rare, and they call this third order. Again, that's not going to make a lot of sense to you because we haven't talked about rate laws or types of rates. So don't panic again about what does that mean. What we want to look at is, and there's that last one, the three molecules have to come together and collide. A reaction is only as fast as its slowest step. And so here, what you're going to be given is a series of steps, kind of like Hess's law way back in enthalpy chapter. I think that was chapter 6 or 7 now. And the rate determining step is going to be the slowest step. It determines the rate law and the molecularity of the overall reaction. So let's take a look at the decomposition of dinitrogen pentaoxide. This can be found by taking a series of small reactions and looking at them. This is the first part, step 1. This reaction also goes on, and I think that you guys can remember from a few chapters ago how to balance these, and then you would want to get things to cancel out. There we go. There's that third step. Sorry. So what you can do is you can take a look at 3 baby steps, so to speak, that can be combined and interacted to make that one overall final reaction step. And you should remember this from a few chapters ago where they're crossing out things that are the same on opposite sides of the arrow. So NO3, NO3, NO2, and then see NO2s on this side. If they're on opposite sides, they will cancel out with one another. And then you have another NO3. Oops. Let's redo that and see what happens here. I feel like the PowerPoint's a little off on this, but hopefully we get to the main idea with it when we're done. Not having a lot of luck. The main thing is that you see 3 reactions here, and that you can kind of see things are crossing out opposite sides, and when they do, you're left as a final thing to match this reaction. What they want you to get out of this is if you're given all 3 of the reactions, or 4 or 2 or whatever, and you know the fast ones that are occurring fast and which ones are occurring slowly, you want to take a look at the slow one, and that is going to be your rate determining step, which again we'll talk about a little later. What I want to pull out of this, though, is that you can actually look at these reactions and find the catalyst from it, and that's kind of where we're going. And we want to be able to find what we call the intermediate step. So again, here's just kind of a generic 3 mechanisms that are happening. You can see one is a fast, one is a slow, and then another one is a fast step. You can see things that agree with each other on the same side or disagree, or are the same on opposite sides of the arrows. Those are going to cancel to give you the final A plus D plus F arrow Z. The B's cancel and the C's cancel. What our goal is in looking at these, this is just generic, is to determine which one of the molecules is going to be what we call an intermediate and which one of these are called the catalyst. And so I'm going to skip ahead one more time with you, so in a minute. But I want you to see what the definition of an intermediate is. And an intermediate here is something that is going to be the C and the X. It's something that was not added. It just appears. And as you can see, like initially you added A and B and you made C. So C just appears. And then it goes on to react with something else, in this case D, to make B and X. And those go on to make X and F to make Z. So these are all like just for fun or for examples. They're not obviously real molecules, but the goal here is to see that what is an intermediate? Intermediate is something that all of a sudden appears and then disappears. Here's X does the same thing. It appears and then it disappears. So it's not part of what you originally added, and it is not a part of your final product. So that's the definition of what an intermediate is. I guess you can consider it, if it appears, it'll be unstable, so it will disappear. So in this particular case, what is the intermediate? What is the final equation? And again, you don't need to know what the rate law is, but I would guess that you can see C all of a sudden appears, and then it's used in the fast step, and then it disappears. So I would say C is your intermediate here. The C's cancel out, the A's add together, the B's are there still, and the D. So just to kind of give you a final, I can't write on this, but your final equation would be 2A plus B arrow D. Your intermediate would be the C. And just to kind of give you a heads up, if you wanted to know the rate law, you look to the slow mechanism to find the rate law, and we'll write those later. Okay, I am going to skip ahead again. So now you know, hopefully, what an intermediate is. You know that there's 3 types of molecule collisions: unimolecular, bimolecular, and termolecular. Those are the different types. And now let's look at the 10th page of your packet. And this is section 12.7, catalysts. And I have kind of a cool demo I'll do. It's called the glowing penny demo that I'll do for you when we come back. But I am going to skip ahead then to, let's see, page 77. On your PowerPoint. And you can see, out of the mechanisms listed below, which is the most consistent with the observed kinetics present, some sort of a logical argument to accompany your choice. Anything not in the final reaction, A, B, or C, could be considered an intermediate. So I'm trying to think about if this is where I want you to be. Because I believe, okay, that was page 9. So never mind, let's keep going. This is where I want to be. All right, so we're at the top of page 10. And we're going to talk about collision model again, still a little bit more. Number of collisions, or the frequency, increases with increasing temperature. We know that. And reaction rate is only a fraction of collision frequency. Only a small fraction of collisions actually produce a reaction because they might not be colliding at the correct orientation. And we also need activation energy to be ample enough for the reaction to occur. So it's the energy which must be overcome for the reaction to occur, and only a small fraction of the collisions have enough energy and have the right molecular orientation. So those are the 3 pieces that we've gone over a few times now: activation energy, orientation, and just energy to collide, so the temperature that they have to begin with. Activation energy is the energy that must be overcome to produce a chemical reaction. And there's always like those videos, or a video you could watch on YouTube. I have a Mac, so they're not playing right now. And collisions, again, must involve enough energy to produce the reaction, must equal or exceed that activation energy. And the orientation must allow for that transfer of energy and the new bonds to form the products.